In today's video, I would like to introduce a very nice problem. So our goal, we are going to determine this series is a converges series or diverges series. Okay, so for this example, we are going to see the harmonic series is written on this form: sub n equals the sum as a finite series as k goes from 1 to the n of 1 over k. Okay, let's see the behavior of this series. In fact, this series is a particular case for the series which is written on this form: 1 over s to the m. Okay, as k goes from 1 to the n, like this. So for our example m equals 1. This one is called the harmonic series. Okay, so our goal, we are going to prove this one is a diverge series. So by the way of contradiction, suppose s as a harmonic series, which is written on this form: 1 over k as k goes from 1 to the n, is a converges series. Okay, I'm going to analyze this series first. S sub n of this sum as k goes from 1 to the n of 1 over k, I can rewrite it as 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, and so on and so forth until you get the last term. Okay, so if you take a look carefully at this expression is associated with the odd and even terms. Okay, so which means s sub n must be written on this form: the sum of s sub n of odd terms as k goes from 1 to the n plus the even terms, the sum of s of n even as k goes from 1 to the n. It's k, like this. Okay, let's call this one as the first method. We know 1 over 2n minus 1 is strictly superior than 1 over 2n. Okay, I'm going to apply the sum notation on both sides. I will have the sum of 1 over 2k minus 1 as k goes from 1 to the n is strictly superior than the sum of 1 over 2k as k goes from 1 to the n, like this. Okay, we know this sum is a odd sum, we know this sum is an even sum, so I'm going to add the even sum on both sides. Okay, so I will have the sum as k goes from 1 to the n of 1 over 2k plus the sum of 1 over 2k minus 1 as k goes from 1 to the n is strictly superior than 2 times of 1 over 2k as k goes from 1 to the n, like this. Okay, I'm going to expand this one like 2. I'm going to expand this one and take this number 1 over 2 as a common factor, so I will have 1 over 2, 1 over 1 plus 1 over 2 plus 1 over 3, 1 plus 1 over 4, and so on and so forth until you get the last term, 1 plus 1 over n as a finite series. Okay, so this half will be cancelled out with this number 2. So we know this sum is a Sn, so which means this term, we know this term also is a S sub n because we have the even terms plus odd terms, so which means Sn is strictly superior than Sn. This one is a contradiction. Okay, which means our assumption was wrong, which means this sum is not a converges sum but is a diverges sum. Okay, this one is a diverges sum. This is method number 1. Let's apply the method number 2. S sub n, as we mentioned before, so 1 over 2 plus 1 over 3 plus 1 over 4 and all the way down to the 1 plus n minus 1 plus 1 over n. Okay, I'm going to apply the integration here. So this one equivalent Sn equals the integral from 0 to 1 of 1 plus x squared plus x cubed plus x to the 4th and all the way down to the xn minus 1. dx. Okay, if I'm going to evaluate this integral, which is giving us, it will giving us x is evaluated from 0 to 1 plus half of x squared is evaluated from 0 to 1 plus 1 over 3 of x cubed is evaluated from 0 to 1, and all the way down to the last term, 1 over n is multiplied by x to the n is evaluated from 0 to 1. Okay, each term of this evaluated integral is a primitive of the original one. Okay, so the primitive of 1, which is x, is evaluated from 0 to 1. The second one, the primitive of this one, is a x squared, half x squared, which is okay, and so on and so forth. The last one, the primitive of this one is a 1 over n is multiplied by x to the n. Okay, so which means this one is giving us this result. Okay, so now I'm going to work on the first expression. What we know about this series, this is geometry series, is also is a converges series, because we have x, because we have absolute value of x is strictly inferior than 1, because x is located between 0 and 1. Okay, Sn equals the integral from 0 to 1 of the sum as n goes from 0 to plus infinity of x to the n dx, with x, the absolute value of x is strictly inferior than 1. Since this one is a geometry series and converges series, which means I'm going to replace, we have x from 0, integral from 0 to 1, I'm going to replace this one with dx over 1 minus x. Okay, this one is a natural log. This is a natural log of absolute value of 1 minus x is evaluated from 0 to 1. Okay, this one is an indefinite form, which means I'm going to apply the limit here. So Sn equals the limit of natural log of 1 minus x is evaluated from 0 to 1 as x is approaching to 1 from the left hand side. Okay, upper bound, which is limit as x goes from 1 from the left hand side, minus the lower bound. The lower bound is 0, because 1 minus 0, which is 1, the natural log of 1 is 0. So but this one we must apply the limit, because we have indefinite form here. So it's giving us a limit of natural log of capital X as x goes towards 0 from the right hand side. Now becomes 0 from the right hand side as x is approaching number 1 from the left hand side, which equivalents the capital X is approaching 0 from the right hand side. This one is giving us minus infinity. Okay, which means this series is a diverge. Okay, this one is a method number 2. Now we have done this problem. If you are interested in watching this one, don't forget to support us with your like and subscribe. Thank you for watching. We will see you next video. Bye.